Tonight's speaker is Dr. Willie Yee. Dr. Yee is an amateur astronomer and past president and member of the board of directors of the Mid-Hudson Astronomical Association. He is presently a solar system ambassador, which is a program supported by NASA and the Jet Propulsion Laboratory in Pasadena, California. He is a retired psychiatrist and a magician trained at the world-renowned McBride Magic and Mystery School in Las Vegas. Dr. Yee has been a Red Cross volunteer for 13 years, maybe more than that now, active in sheltering, mental health, community relations, and teaching. Dr. Willie Yee's topic for tonight is titled White Dwarfs and the Fate of the Universe. So let's give a warm welcome to our speaker.
Okay. Solar System Ambassadors is a program sponsored by NASA and JPL. They support us in terms of educational stuff and goodies to give out. But that being said, my views do not represent that of NASA or JPL, which lets me say all kind of nasty things if I want about the administration. All right, so tonight we're going to talk about white dwarfs. What is white dwarf? No, not you. A white dwarf is a stellar core remnant. It is a collapsed core of a sunlight star. The original star, okay?
Just keep going. I'm just going to change the presentation.
The original star is between 0.4 and 8 solar masses. Below that, we don't get stars. Above that, they're too big to become white dwarfs.
Yeah, I did it wrong. Keep going.
Okay. They are the smallest and densest currently known objects in the universe other than neutron stars and black holes. How dense? The mass of the sun squeezed down to the size of the Earth, meaning 1 teaspoon of white star matter would weigh 2.5 tons, would weigh 5 tons. So we could put all of the birthday parade into a Volkswagen if it were made out of white dwarf stars. So where do white stars come from? And where do white star talks come from? I've previously presented on black holes, and I said, that's interesting. Well, what about neutron stars? And I gave a presentation on that. And obviously, the next thing on the list, well, white dwarfs, they must have some interest of themselves. So basically, if the mass of the star is over more than 25 times the sun, it will eventually end up as a black hole. If it's between 8 and 25 solar masses, it'll end up as a neutron star. If it's between 0.4 and 0.8, it becomes a giant star, then a red supergiant, then a planetary nebula, and ends up as a white dwarf. Below that, we get red dwarfs, brown dwarfs, and Jupiter. Okay. So what determines the size limits of things? Let's start at the bottom of the list. Black holes, the size limit, it's a singularity. It has no size. Neutron stars, the size is determined by neutron degeneracy, which means how dense can you pack neutrons before they no longer become neutrons? Basically they break up into smaller particles, and you might even end up with a quark soup. White dwarfs are determined by electron degeneracy. So what is electron degenerate matter? Well, it's part of this whole process that goes through almost everything we talk about stellar evolution, the struggle between thermal energy, heat, and gravitation. When the thermal pressure is not enough to push things apart, you get gravitational collapse. At a certain point, the electrons are no longer bound to the nuclei. And then what happens to the electrons? Well, the Pauli exclusion principle, if you remember your chemistry, says you can't get more than 2 electrons with different spins in the same space at the same time. And what's going to happen? Well, the other thing that happens is they go up to the next highest energy state. And since everything's already squished in at the lowest energy state, they have high kinetic energy, which means they start exerting pressure back the other way. So degenerate matter means the electrons are not bound to the nuclei. They're not behaving normally because of the intense pressure. The electrons all want to go to the quantum energy level. They end up going to higher levels, and this counteracts gravity. Gas laws, remember Boyle's law and all that thing, temperature and pressure, that doesn't apply anymore because those things depend on things being organized into molecules. These electrons, because of this, again, under great pressure, great kinetic energy, and they start to move at relativistic speeds, close to the speed of light. And we know when that happens, miracles happen. For instance, since these electrons are moving at near the speed of light, they get smaller. So as you increase the mass, and here's where EM square is happening, they actually get smaller. Although, again, putting out tremendous amounts of energy. The Chandrasekhar limit, which I talked about in some of the other talks, is the limit at which a white dwarf can no longer become a white dwarf because the mass is so great it collapses into a neutron star or a black hole. That limit is about 1.4 solar masses. So we might start out with 8 solar masses in the sun, but by the time it all blows up and all turns into energy and planetary nebula and gas and everything else, at most it could be 1.4 solar masses in mass. So the characteristics of white dwarfs, well, mentioned density, low luminosity because there's no fusion or very little at this point. So we're talking about a dying star. It's gradually cooling, very gradually. Its size is 1 to 2% the radius of the sun. And again, it's composed of plasma. So strange stuff that's not gas. The basic structure of a white dwarf is a core of hydrogen and a core of carbon and oxygen, which is the end product of fusion in a star this size. Unfused helium will be in the next shell, and around that there will be a hydrogen shell. And the hydrogen shell will generate most of the light that we do see in the star and what we do spectroscopy on. But there is some variations. And this is not showing my graph at all. Anyhow, we'll forget the graph. The variations can be, as we said, the basic structure, hydrogen, helium, and a core. Some white dwarfs, all the hydrogen's been blown off, and the surface is either helium, which we call a DB, or DO, which is ionized helium. So there's still some energy going around there. And in some objects, all of that seems to be blown away too. We just have an exposed core of carbon and oxygen, and these are pretty dark objects. There's some other sub-classifications, but this is basically what's going on. 10% of white dwarfs have a magnetic field. This is not really completely understood. Source is unclear. One possible source is the original star, like our sun, has a magnetic field. And so there may be some conservation of momentum, magnetic momentum as it collapses. And so the magnetism remains. It could also be a consequence of mergers. Often, usually when things merge, they don't hit head on, they hit kind of sideways, and everything ends up spinning. So when you start spinning stuff, especially ionized stuff, you generate magnetic fields. There may also be a process of crystallization or convection going inside, interior to the star. This is not well understood. We can't see the inside of the star, so it's a little hard. One of the things that's believed is if there's a strong magnetic field, it could raise the Chandrasekhar limit, so you could have more than 1.4 masses in a white dwarf. So again, big stars turn into neutron stars or black holes. Average stars, like our sun, eventually swell up to become red giants. In the case of our sun, probably around the orbit of Mars, so they get really big, but then diffuse and then collapse into a planetary nebula and end up with a white dwarf. So what happens to white dwarfs, again, depends on their mass. If it's below 0.5 solar masses, it cannot fuse helium. It'll burn all its hydrogen, but not, and will just leave helium-4. It becomes something called a blue dwarf or a helium dwarf. They last longer than the age of the universe, which we'll get into a little more later. If it's a little larger, between 0.5 and 8 solar masses, at the end of hydrogen fusion, everything blows up into a red giant. Helium is still getting fused into carbon and oxygen, but there's not enough density to fuse carbon to neon. And at the end, we end up with our carbon oxygen core, a helium burning shell, an outer hydrogen shell. And lots of material expelled, creating the planetary nebula, which we all love to see and take pictures of because they have an enormous amount of variety. But in the end, only a carbon oxygen core. There are some that can fuse into neon, and we can have something called a neon nova. Again, if it's the mass is larger than 1. It starts out as more than 8 to 10 solar masses, it's more likely to collapse into a neutron star or a black hole. Much of the interesting stuff about white dwarfs and much of what we've learned about them comes from binary systems, because we've talked about all this nice timeline of stellar evolution, but this throws a monkey wrench into the whole thing, because now all of a sudden you're adding more mass to this object and therefore changing its characteristics. If a white dwarf is sitting near another star, perhaps a red giant, and gradually taking gaseous material into it, eventually it starts accumulating that into its mass. Its mass increases. Eventually it exceeds the Chandrasekhar limit. If, as usually happens, this thing is spinning very rapidly, apparently you can exceed the Chandrasekhar limit, because spinning keeps things from collapsing quite as fast. But eventually the spinning slows down. Now you've exceeded the limit, and boom, we end up with a nova, a type 1 supernova, which have the wonderful characteristics of always being of approximately the same energy and size. So it's exactly when you exceed that limit, which is a constant, you get a supernova. And this is why they are so valuable as a standard candle, so that we know when we see a supernova, we know how bright it is, how far it is out there, and from how bright it looks to us, we can now calculate its distance. And this enables us to do things like calculate the distance from the distance of the to the edge of the universe. After this boom, since it's exceeded the limit, it goes back, it collapses into a neutron star or a black hole or maybe blows apart completely into a diffuse nebula. If two white dwarfs come close together quickly, they immediately go straight into a neutron star. Other interactive events with white dwarfs. If there was an interaction with a black hole, basically the black hole would eat the star. It would create X-ray flashes, lots of radiation. We would know about it, but nobody's seen one yet. But there's been much modeling, so we have a pretty good idea of what it would look like and how the black hole would behave in such an event. What kind of radiation would be thrown off? What kind of debris would be thrown off in this event? So this is one thing people are still looking for. There are also widely separated binaries, so they're far enough apart that they don't exchange material, but they orbit a common space. And you can subtract the age of one of its progenitors from the other's mass and link that to its mass. And this may be one of the ways that many white dwarfs have such a wide range of masses, because you may be looking at two white dwarfs, so they may not be all that easy to resolve, in ordinary astronomical observation. Colliding white dwarfs can create a wind of lots of stuff being thrown out. Again, things collide, they start spinning. Magnetic fields get developed. This creates a wind carrying material around and perhaps into jets and bubbles and stuff like that. And a lot of material gets blown out from this interaction. Other interactions, collisions with exoplanets. This material will show up in the spectroscopy because it will be scattered around the surface of the white dwarf. And so we'll get spectral lines indicating other elements. In the case of this beautifully named WD 0816-310, the strength of its light output varies. So we think that's because there's a scar on the surface, much like you have a sunspot, there's a scar on the surface from the material of a collision with a planet or other object. And it's rotating, it's correlated with the magnetic field. And so this probably indicates that the scar tissue got funneled by the magnetic field near the pole. So let's look at the timeline of stellar evolution. From the molecular cloud to a protoplanetary disk, it's several million years. It takes about 100,000 years for this stuff to flatten into a disk. And then in 3 to 10 million years, planets start to show, things start aggregating into lumps. One lump in the middle becomes the star, and in 50 million years, fusion begins, and we now have a sun. Over several 100 million years, there's the heavy bombardment. All these lumps of stuff that accumulated in this disk and turning into planets are bouncing around like billiard balls and creating lots of craters on different objects. Then the sun-like star lasts about 10 billion years. So our sun's got about 6 billion years to go. Relatively short in astronomical terms, the red giant phase lasts 100 to 200 million years as this thing blows up. And then starts to cool from 120,000 degrees Kelvin to 40,000 degrees Kelvin over 3.5 million years. But then it becomes a white dwarf. And for some reason, they cut off the graph here at 14 million years. Where is the other end of this graph? At this scale, it's in Chicago. The white dwarf will last all that time, trillions of years, maybe a quadrillion. So all of this stuff is a flash. This is barely a birth pain in the life of a white dwarf. Some white dwarf facts. 8 of the closest 100 star systems are white dwarfs. The nearest is Sirius B, so we can see these on telescopes. 97% of Milky Way stars are white dwarfs. Why is that? Because they last so long. All the others only last, a few billion years, but these things are going to go on and on and on. So we've got lots of white dwarfs around. They have varying amounts of hydrogen atmosphere. The core is supposedly isothermal. If that's so, then how do we get this crystallization and convection going on? This is all a matter of modeling and stuff since we can't observe it. 10% have magnetic fields. And in the formation going from star to red giant, planetary nebula, we generate elements. This is my favorite periodic table because it shows where all the elements in the universe come from. So if you got a piece of iron around right there, that's a result of a white dwarf supernova. Huh?
They can't see the laser.
They can't see the laser.
No, if you use
If I use the mechanical. Okay. All right, so we go look at iron. There we go. Okay, there we go. So iron is a result of a white dwarf supernova. If you've got any gold, you have the result of merging neutron stars. So all the star stuff and carbon, of course, dying low mass stars. So something on its way to a white dwarf created the carbon that we are all made out of. So we're all made of star stuff. And this is the kind of stuff it came in. So cosmic ray collisions cause some things. Some things are dying high mass stars. The Big Bang gives us hydrogen. Like our periodic chart here is very incomplete because we've already got up to oganesson, which is element number 118. All of 5 atoms have been created in all the research, and that everything we know about this. So we don't know what its crystalline structure would be. There's, we can do all the modeling from all the other elements, and the half-life of these atoms are less than a millisecond. So oganesson has lasted for less than 1 millisecond in their lifetime. Many of these other elements down here are man-made, but I digress. So what happens next? So we start from somewhere between 8,000 and 4,000 degrees Kelvin. We haven't observed anything cooler than that. Why? Because we haven't been around long enough to see the white dwarfs cool that far. So eventually it does continue to cool and then goes on for trillions of years and ends up as a black dwarf, not giving out any energy at all. So what's going to happen next? Well, now if we're talking God trillions of years, we're looking forward to the end of the universe, in which the final objects will be black holes. I mean, if we have these empty black things that are left over from dwarfs, they're all eventually going to coalesce because of gravity. And so what's going to be left is black holes. Long before that, in 17 billion years, the universe will have so expanded that light will not have time to get back to see anything. So the universe is going to go dark long before it dies. In 100 trillion years, the stars will stop forming. All will cool and go back. Present theory is that the universe itself may last a googolplex of years. So 10 to the Google years. So when we learned this number in math, we thought it was a totally useless number, but it gives us an idea how long the universe is going to last. So we're going to be around for a while. Don't panic. On the other hand, long before that, we'll get eaten by the red giant. So where's our research headed? Well, we like to know a lot more about the internal structure of the core and how that correlates with internal structures of stars and everything else. What is there an action of convection? What are the effects of accretion? As before the star goes supernova, a 1A supernova, what's happening around the surface of the star as it keeps gathering all this gas from another nearby star? What are the effects of magnetism on that in those objects that have magnetism? And what kind of weird chemistry is going on with helium under these circumstances? Can we duplicate any of the conditions of a white star in the laboratory? Well, they're trying. Here's the Z-Pulse machine at Sandia National Laboratories. You look at the stairs there to give you stairs right here to give you an idea of the size of this thing. But then there's the National Ignition Facility at Lawrence Livermore, Mass. Now here's the entranceway. Here's the doorway. So this is roughly a one-story building. All the rest of this stuff is energy generating, coils and magnets and whatnot, all converging on this one point. So these enormous charges of energy get built up, all shot and compressed into one space, and then lots of detectors around to see what all comes out of it. So some things, some of the radiology and kinetics and chemistry may occur in or around dwarf stars, and can learn a few things about that. So what good is this? Well, knowing that there are white dwarfs, we can get an age determination of a stellar population. So if we have a globular cluster, we don't know how old it is. Well, how many white dwarfs you got there? Similarly, it can help us determine the age of galaxies. If we start to understand dwarf stars, we may understand the physics of stellar interiors. And when exoplanets get eaten by white dwarfs, their material is still distributed around the white dwarf, and we can get their spectra, so we can still be studying what that planet was, some things about that planet before it got drawn in. So what have our NASA missions taught us? Hubble's been able to detect the oldest dwarf stars, which formed 1 billion years after the Big Bang. And this gives us another indicator of the age of the universe. And at this point, I want to put in a plug for Hubble. Everybody thinks Webb has made Hubble obsolete. Wrong. Hubble can see in the ultraviolet. Webb cannot. So there's a whole bunch of information that can be gathered from Hubble. So Hubble is still and will continue to be very active and very contributing to science. It is not obsolete by any means. Here's an image of NGC 2440. You can see this in a good sized telescope. It's magnitude 9. Its star is in the middle, and that's magnitude 17. So you need a big telescope. See that? Its temperature is 200,000 degrees centigrade or Kelvin, which makes it one of the hottest objects known, certainly among planetary nebula. Hubble was able to measure the gravitational redshift around Sirius B. So again, another confirmation of the theory of relativity. And with that information, we can tell that the sun, the star of Sirius B, is about 98% of that of our sun. So very similar in size to the sun. Here's an image of a galaxy cluster, over 5 billion light years away. If you look at this picture, we're seeing a galaxy here, and around here is lensed another galaxy from behind it, and it has a supernova in it, which shows up in 4 places as the light gets bent around the lensing galaxy. So Webb has been able to detect exoplanets around a white dwarf. Here is an image from the medium infrared camera. If we block out the image of the star, we can detect right here an object, and that is the candidate for an exoplanet. Similarly, around here, the candidate exoplanet is here, and we can subtract that and see there's nothing else there. So we have evidence that there are large planets. If the large planet's far enough away, I don't know exactly how far, it means that they can survive a star going through its red giant phase and then collapsing and whatever, and the planet will continue on its way. Webb has also been able to detect a debris disk around the white dwarf. This is an artist's conception. We don't have an image of this. We do have spectra of stuff, rock, calcite, malachite, and sodium bicarbonate. So there might have been water on this thing at some point. So this is the remnants of a planet smooshed around a white dwarf. When we look at spectra at white dwarfs, some strange things happening. If we have the same chemical creating a set of spectral lines, when you look at them at the white dwarf, aside from redshift, the lines are still there, but they get smooshed and they become broader because of the enormous gravity is distorting everything. And again, a little bit of relativity comes in here to gravitationally bend light and alter frequencies. So the frequencies are still there, but the blank spaces, the absorption lines changes. The chemistry is a little bit different. So here's some Webb images of planetary nebula, Ring Nebula, which we can see in a telescope, the Southern Ring Nebula. Again, depending on what frequency we're looking at, these objects look very, very different. Okay, we're almost done here. My sources are Wikipedia, directly stuff from NASA.gov. If you want to see the paper that most of the latest, well, this is actually over 10 years old now. You can read this paper on current challenges in the physics of dwarf stars to see what people were thinking about what they want to study. So take home points. A white dwarf is a remnant of a star. It's dense. The white dwarfs are varied in structure. They're numerous, most of the stars in the Milky Way, and they live a long time. And they are the source of many of the elements that we are composed of and that our planets and most of the universe is composed of. And that's it. I have any questions? Okay, thank you.
I have one.
Go ahead.
In the core of white dwarf, it's carbon and oxygen. And are they like nuclei surrounded by electrons? I kind of missed that.
The core of a white dwarf would be plasma. So so you'll have nuclei of carbon and oxygen floating in this soup of electrons that are not in orbitals around them. So it's just this big soup of stuff.
Okay. Thank you.
So I was trying to get a sense of what the white dwarfs radiate, what the emissions are, and it sounded like the hydrogen is actually in a simple combustion phase, and there's some fusion happening.
There's still some fusion happening.
And also possibly some photon emission from simple cooling.
Yep.
So anything else? Did I miss anything else?
That's probably most of it.
Okay.
You know, I suspect there's other levels all the way up to gamma radiation, but it's very weak. It's probably much weaker. Certainly not compared to something like a supernova, where you get gigantic bursts.
Further questions in the room?
Hey, Willie.
Was there one on? Go ahead.
Yeah, Willie. In your graphic that you say would end up in Chicago, have you considered using log graph paper? That'll simplify it.
Logarithmic scale.
Hmm?
A logarithmic scale for
It-
the timeline.
Yeah, well, yeah, we could squeeze it down there that way. It's more dramatic this
Wouldn't
way.
be nearly as
Yeah,
impressive.
I know. True.
Yeah.
So this is partly a comment, partly a plug for my upcoming ARP talk. But today, literally, I was reading some of the sociology of the internal politics of the Mount Palomar Observatory. And it turns out they were talking about how Alan Sandage, who essentially ran the observatory, made a terrible mistake in that he mistook blue dwarfs for quasars. And because they actually, in the early 60s, when this was going on, they look a lot alike because they're small and they're dim. But it happens the quasars are billions of light years away and the white dwarfs are hundreds of light years. And so I was partly confused by a blue dwarf. I've heard of a white dwarf, but you answered that question. So thank you very much. And this was relevant to the ARP research because ARP and Sandage were in the same lab. And ARP had written a paper that explained in part that you had to be really careful not to confuse blue dwarfs with quasars, because he was looking at quasars too. And Sandage, because he ran the lab, a paper he wrote jumped the queue and was not peer reviewed and had this terrible error, and Sandage actually offered to resign because of it. So and set up kind of a lifelong tension between him and ARP.
Well, sometimes folks are wrong. The story of Chandrasekhar is just as interesting because he developed this. He did all the math in the 1930s, everybody put him down, most notably Sir Arthur Eddington, because the implication of the Chandrasekhar limit was there was such a thing as a black hole. And Eddington says such a thing can't possibly exist. This is bullshit physics. Forget it. And he went for 20 years before somebody finally recognized that he had done this and that it made sense and it was accurate. And he ended up getting his Nobel Prize after he'd actually left the field for a lot of that time because he was so ostracized because of this. He did eventually get a Nobel Prize. Yeah.
I have a comment and question, I guess, both. I had no idea that that most of the stars in the universe were white dwarfs. I imagine, though, that when you look at something like Andromeda, that's probably not what you're like. The brightest stars are obviously not the white dwarfs. You're seeing more of the brightest stars when you're actually looking at a picture than the white dwarfs. They just make up I guess the glow. But yeah, I was surprised at that. And I guess it's not that surprising that although there are a lot of white dwarfs out there, we're made of the stuff of white dwarfs, but the only way to get the stuff distributed is for them to blow up, essentially. And enough of them, I guess, have blown up to distribute their chemicals throughout the universe. But
Yeah, so we're on the third generation of stars, so all that stuff's happened and reaccumulated.
yeah, but the number of times that's happened compared to the number of stars is relatively low. Obviously, most of the white dwarfs have not blown up or anything. They're still there.
Well, of course, over a whole generation of galaxies, how many of them bumped into each other and
Right.
got eaten by black holes and
Just
whatever,
enough.
who knows?
I have a question. If you mentioned rogue planets around white dwarfs, which begs the question, can smaller planets also exist around them? And if so, do white dwarfs have a habitable zone?
That's a good question.
Yeah, that's a good question.
Because saying like brown dwarfs, for example, have a habitable zone, be much closer in, but
Yeah,
and much smaller. But I'm just wondering if the same might apply for white dwarfs.
there's no reason it couldn't, although again, there's this balance of heat and gravity. And where's that point going to be where those things are balanced, where you can be in a stable orbit and not get incinerated?
Yeah, and do they generate more UV than our sun? I would imagine they do per unit of heat, I guess.
Yeah.
And you could be in a habitable zone, but then you'd be too close to the UV, and then
Yeah.
if you get far enough away to be safe from the UV, it would be too cold. So yeah, that's a good question.
Yeah.
There's a question from the chat. John asks, is it possible for a white dwarf to have jets like a pulsar?
I don't know, but I don't think so. I think it's unlikely because they don't have that much energy to spin around and generate. Don't forget, a pulsar is a neutron star, so it's a lot more mass and things are moving a lot faster and a lot more energy. So it's probably less likely that they would have a jet.
Yeah, I have a comment myself that you've pointed out that there are so many white dwarfs out there, although we don't really see them. And from what I understand, the estimate is that at least half of them are in binaries. And those binaries are causing gravitational waves. But the frequency of the gravitational waves is much lower than what LIGO can detect. LIGO is tuned for black hole collisions, not smaller, and maybe neutron stars. So when LISA finally turns online, they're expecting a cacophony of gravitational wave signals coming from the binary white dwarfs.
that will be a challenge. Because don't forget, 8 of the nearest 100 stars are white dwarfs. So it's going to be a lot of
Well,
noise.
so that, I don't know the answer to this, but it makes me wonder what the gravitational wave signal would be from Sirius, with Sirius A and B being a binary. They're not the same size,
Yeah.
but that's a
But
calculation.
that's,
I could.
yeah, that's such a slow orbit though. I mean, the period, it's what, a 50-year orbit. So you get one wave every 50 years, right?
Yeah, that's a very low frequency, but
Yeah.
that's
And probably very, very low energy too.
so. The other comment I have is from you said that reference was 10 years old.
Born 10 years old. It's 2009. So it's
I
like
don't think so.
16, 17.
From what I saw,
I think it was 2009.
can we go back to the reference? There, no. There, archive
2209.
09. So that's actually 2022,
So it's only
September of 22.
so it's only 3 years old.
So it's only 3 years old. Yeah. And then the number after that is just count how many papers there are. So it's yeah. So it's you're actually more up to date than you thought you were.
Right.
Cool. You actually anticipated one of
Another
my
question
questions.
over here.
Where is it? Oh, perfect.
Thank you. Could you explain in this context what's going on with regular nova like Corona Borealis?
What's going on with regular nova?
Yeah.
That was my other question.
Oh, good.
Regular nova they're part of regular stellar evolution on their way to I forget.
Well, so Corona, T Corona Borealis is a partner with a red giant.
Mhm.
It's a white dwarf, and it has a red giant, and it keeps sucking material off the red giant until it gets enough material to cause nuclear ignition.
Mhm.
And that burns off the material in about a week.
Mhm.
And then it goes back to just being a white dwarf going around a red giant.
So why wouldn't it? You said earlier that if enough material accretes, it would become a neutron star. Why is that not happening with that star?
That's a really good question. What it may have to do with how far away it is from the other star, so how rapidly that stuff accumulates.
Remember, it's the red dwarf is very diffuse, and it's taking just enough to build up a shell that can ignite. So it's not. I actually don't know. If that happens enough times, will it suddenly go over the threshold and become a neutron star?
Yeah, and that was my second question. Like, what would the effect on the white dwarf be over time?
And I don't know.
Okay, that's a fair answer. Yeah.
I've heard that's a really good question to try and find out.
You mean if it was an ongoing recurrent nova?
Yeah, it might build up.
It might eventually build. Well, it depends on the orbits of the star. If they're in decaying orbits, eventually it'll get to the point
How
where.
big is the star that it's eating?
Yeah.
Is that star big enough to bump it up and to level it up to the next, or not? In which case it'll just suck away part of the red dwarf, and eventually there won't be anything to suck away, and that red dwarf will become a white dwarf. And here's a white dwarf, and now you get a binary white dwarf, and they make gravitational waves. I like that story.
And then the last question, sorry to hog the mic, is if you had two white dwarfs collide with enough mass or the right material, get a fusion reaction like start back up?
No, because the mass would be so big that it would go straight into a neutron star. Everything's already plasma, so boom.
Yeah.
It's the cinder. It's
Okay.
It's the remnants, and so yeah, when they merge, you get neutronium. You get neutron star.
Okay. Thank you very much.
Yeah, what I understand with TCRB though is that what's happening is it's pulling hydrogen off, and then that hydrogen is starting to fuse, And that's what blows it all away. And then it starts over again and does it again 80 years later. But 80 years is, as you said, nothing in the time of this thing. Questions in the room?
Do we have time for a magic trick?
Any further questions on the Zoom room? Okay, we're gonna move to magic.
All right.
All right, just be sure you're on camera.
All right. I need a volunteer to help me just move things around here. I will not do anything that will expose you. And I'm going to need people with calculators. So pull out your cell phone and pull up your calculator app. If we want to make this experiment really interesting, somebody could do it with Siri, and somebody else could do it with OpenAI. So you can see what kind of results we get from that. What we have is these columns of numbers. Why don't you come on over on this side? And if we add them all up, we get a number. In this case, we would get 4 9s, 13, 20, 25. Yeah, so this would be 25. Where can we move over here? Where do you want us? You're on this one. Yeah, you're over here. Okay. Now, all right. So, somebody got your calculator? I'm going to stand. I want you to stand right in front of here so nobody can see. And we'll take those two. And take any two of these and arrange them in any order
You want me
you
to,
wish.
I get to twirl.
You get to twirl them and set them up. And so no one can see them, including me. And everybody got your calculator ready? Anybody doing Siri? Nobody has OpenAI? All right, are you ready? Now, when you get the answer, hold your hand or your cell phone up, okay? You're gonna have two-digit numbers. Add them all up. So it's just a matter of addition.
Okay, I should move out of the way.
Okay, are you ready?
Yes.
Okay, go. Anybody got an answer? What's your answer?
Oh, I thought you were holding it up.
Oh, no.
He's got.
I've got it.
What do you got?
246.
246. All right, now let's make it more interesting. Pick up 3.
Okay.
Don't let anybody see. Everybody got your calculators? Are you ready? Okay, I'm ready. All right. Okay. I'm done.
I can't see the bottom 3 numbers.
577, the bottom 3.
Thank you.
There we go.
You move them back so that we can.
Let's start moving.
Ah, excellent.
Now the-
Okay, somebody
now
got
it's
an
tracking
answer?
Whoever.
Stop that.
2846.
Yeah, right, correct.
Now we're doing 4.
Now let's do 4.
I got the pattern here.
Mix them around, turn them around any way you want.
They have to be right side up though.
Now, see who can beat me.
I know, I'm moving.
I was thinking of bringing an abacus, see if anybody's good enough with an abacus to beat me.
Slide rule.
Not so good for addition.
Tell me when you're ready.
I'm ready.
All right, our contestants, are you ready? All right, ready, set, go. Done. You got it? Anybody got it yet?
I got it.
97.
What do you got?
24,785.
685.
24685.
I get 24685.
Okay,
Oh, I guess I made a mistake.
Me too.
all right. Let's try it once more. Only I'm going to stand on this side, so I can't even see the numbers. All right.
Okay.
Are we supposed to be adding all the numbers?
Yes.
Yeah, yeah.
I'm using Chat GPT.
Three, 3-digit numbers.
Okay, you ready? Okay, go.
7 plus 9 plus 9 plus 3 plus 2 plus 2 plus 3 plus 8 plus 6 plus 4 plus 7 plus 4 plus
I got
9
it.
point 7. Nine plus 7 plus 6 plus 7
No, they're 4
equals.
numbers. Maybe that is the other algorithm.
You got it? Who's got it? Anybody got it yet? Okay, what you got?
26,472.
There you go. All right, thank you very much. See you next month.
Thanks very much. We'll see everybody, those who wish to join us at the Follies. Beyond that, our party this Friday night.
Yeah, maybe I'll see you then.
Come up, talk to us. Thank you.
All right, guys.